If you haven't already, please print the handout. We're going to talk about acids and bases, and to start off, let's look at some different properties of acids and bases. So let's list some common examples. What would be the taste, the texture, the conductivity, the pH, and we'll talk about indicators, corrosion, and reactions with metals and carbonates. So some examples of acids, which I'm sure you're familiar with: lemon juice, battery acid, and vinegar. Those are all types of acids. On the base side, we have ammonia. So this would be what's typically in window cleaner, like Windex. You've got soap and detergent, and baking soda. So that reaction between vinegar and baking soda is an acid-base reaction, which we'll talk about in a later lesson. And if we're comparing the taste, acids are generally sour. Think of lemon juice as our example, and not so much the battery acid. I would not recommend tasting that. Bases are generally bitter. I don't know if you've ever had to have soap in your mouth, if you've said the bad word or something like that, but it tastes pretty bitter. Or if you tried eating some baking soda, you could try that and you'd see it tastes very bitter. If you think about bases, like the soap example, they're slippery. So bases have a slippery texture. Acids, they don't really have a characteristic texture. Some of them feel a certain way, some of them feel a different way. There's not any consistency there. Both acids and bases are conductive when dissolved in water. Acids have a pH of less than 7, bases have a pH of more than 7. We'll talk more about pH later. There are different indicators, something you can add to the solution to see if it's an acid or a base. So if you use blue litmus paper and it turns red, that means it's an acid. If you use red litmus paper and it turns blue, that means it's a base. Now you can also use an indicator called phenolphthalein. That's a fun word to say. But if you add phenolphthalein to your solution and it remains colorless, that means your solution is an acid. If you add it to your solution and it turns pink, that means your solution is a base. And if we think about corrosion, an acid will corrode metal, and it will also corrode tissues like your skin. Bases, on the other hand, they will corrode your tissues, so your skin, but not metals. So that's how acids and bases are different for corrosion. Acids react with metals, as we know, but the reaction produces hydrogen gas. When acids react with carbonates, like calcium carbonate, sodium carbonate, things like that, carbon dioxide is produced. This is kind of like what happens when you react vinegar with baking soda. There's lots of bubbles. That is carbon dioxide. Bases don't react with metals, and they don't react with carbonates. So there you have a big overview of different properties of acids and bases and how they're different. And as I say here, there are a few different theories to explain what makes an acid or a base. Meaning, on a chemical level, what differentiates an acid and a base? Well, there's different theories. We're going to talk about one of them in this course. If you go on to further chemistry courses, you'll talk about different theories of acids and bases, but we're going to talk about the theory that Arrhenius came up with. So according to his theory, an acid is a substance that ionizes to produce H+ ions when dissolved in water, and a base, when it's dissolved in water, dissociates to produce OH- ions. So an acid, when dissolved in water, will make hydrogen ions, and a base will make hydroxide ions. Now, just some terminology here. The difference between ionizing and dissociating really refers to what the starting material is. For example, an acid starts as a molecular compound. So here we have HCl as the example. hydrogen and chlorine are both nonmetals. So this is a molecular compound. Whereas a base starts off as, in this example, we have sodium hydroxide. It's a metal with nonmetals, so this is an ionic compound. So HCl ionizes to make ions. Sodium hydroxide dissociates. It's already an ionic compound. It already has ions in it. So the ions just dissociate. So there's a slight difference in terminology, but the general idea is the same. The acid is producing H+ ions in water, and the base is producing OH- ions in water. Now, as I mentioned, this is one theory as to what an acid and a base are. And as with any theory, there's some problems. So the big three problems are there are some acids that don't contain H+ ions. So that's a big problem because according to this theory, acids produce H+ ions in solution. The other problem is there are some bases, like ammonia, that don't contain OH- ions in solution. Well, that's another big problem because that's the definition of a base according to this theory. The other problem is that there are some acid-base reactions that don't occur in aqueous solution. So this theory defines an acid and a base based on what happens when they're dissolved in water in an aqueous solution. So because there are acids and bases that don't exist in aqueous solution, that's a big problem with this theory. So as with any theory, there are problems, and this is why we have other theories to kind of fill in the gap. But for us, this is the theory we are going to proceed with. So I'll ask you to flip to the next page. I'm going to spend a little bit of time talking about the pH scale, and you might be familiar with the pH scale already, so this might be a little bit of a review. But basically, the pH is a commonly used system for representing how acidic a substance is. So the scale ranges from 0 to 14, or very acidic to very basic. Now in the middle of that scale is 7, and that's the number you got to remember. pH of 7 means the solution is neutral. It's not acidic and it's not basic. It's in the middle, neutral. And the pH of a solution indicates the concentration of H+ ions. Now it's not telling you what the concentration is directly, it's what we call a logarithmic scale. So mathematically, to calculate the pH, you would take the negative log of the H+ ion concentration. That's what those square brackets mean. It means the concentration of H+ ions in moles per liter. So I would encourage you right now to take out your scientific calculator and try to find the button that says log, because that's the button that you will use right here. And just remember, this is the molar concentration, which means moles per liter. It has to be in moles per liter, or else this doesn't work. So I want to show you now how you can calculate the molar concentration of hydrogen ions. And it's basically the opposite of this equation. If you've ever taken grade 11 functions for math, this will make a lot more sense. But basically, to undo a logarithm, the opposite of that is 10 to the exponent of whatever. So if you know the pH, you can calculate the molar concentration of H+ ions by plugging in 10 to the exponent negative, whatever your pH is. And I'll just show you this. I'm not going to use it a whole lot here, but we know what pH is. There's also something called pOH, and the total between the two is equal to 14. So for example, if my pH is 7, that means the pOH is 7 because the total has to be 14. If I have a pH of 2, that means my pOH would be 12. So you might see that, just not from me any further. And a couple things, because pH is a kind of a measure of the hydrogen ion concentration, you can change concentration by dilution. So if you dilute your acid or your base, you're going to change the pH. The other thing would be neutralization. Now, neutralization is just the reaction between an acid and a base, and the end result would be a neutral pH. So if you have an acid and it has a low pH, you can add a base and that will change the pH to be more neutral. And with all that being said, let's try some examples. So first off, this question says, calculate the pH. I'm going to stop right there. To calculate pH, remember the formula I just showed you. pH is equal to negative log of the hydrogen ion concentration. So let's continue in the question. Calculate the pH of vinegar. Its hydrogen ion concentration was measured to be 6.2 times 10 to the negative 3 moles per liter. So this concentration is already in moles per liter. That's good. That means we can take this number, plug it into our equation, and solve for pH. So you should get an answer of 2.2. So this would be very concentrated vinegar if it has a pH of 2.2. If you're not getting this number when you try it in your calculator, that means you're probably plugging it in to your calculator wrong. Some common mistakes would be not putting the brackets around your number here or typing in the scientific notation incorrectly. So you'll just have to watch for that, and if you're having troubles, you can send me an email and I can help you figure it out. The second example, though, is calculating the concentration of hydrogen ions. And this time we know what the pH is. So we use the formula for calculating the hydrogen ion concentration, and we're going to plug in 3.3 for the pH. And you should get an answer of 5.0 times 10 to the negative 4 moles per liter. Don't forget your units in your final answer. So if you're having trouble with any of that, send me an email. Otherwise, you can move on to the next part of the lesson.